Alright guys, we're going to take a look at Milwaukee's new premium line of levels. They're branding it the RedStick line. This is their 48-inch line. They've got a compact version that doesn't have these handles. And they've gotten it in lengths, I think, up to 96 inches and then down to 18 or 16 inches, I think. So this is their premium line, like I said, and this one runs you MSRP $170. That's a little bit more than their competition. They're going after Stabila. They call it out on their label. It says stronger than Stabila. That's throwing down the gauntlet, in my opinion. But the Stabila one that's roughly comparable to this one is 155 MSRP, and I've seen it for as low as 100 elsewhere. So I don't know if Milwaukee's going to eventually discount this one. But for right now, this is quite a bit more expensive than the competition they're going after in the premium construction level market. So features they're claiming, I mean, they've got these nice oversized handles. I can fit my hands in here with gloves on, no problem. So it's easy to grab, easy to hold. They've got nice, really visible, really bright, big, impact-resistant vials here, branded Sharpsite. It's got a hanging hole right here, shock-resistant end caps, and then on this model you also have magnets. They have a non-magnetized model of all of these as well. So, things I like about this, these end caps are removable without tools. You just grab this center plastic tab and pull up. However, I don't think they're quite as shock absorbent as the Stabila levels. I've seen Stabila reps drop the level and it bounces like almost back to where they dropped it from. This one, if I drop it, it recovers about a foot. I mean, it recovers about an inch out of every foot. It still feels pretty impact absorbent, but I think it could use a little bit more rubber because these outside pieces are rubber and they stick up about a 32nd of an inch past this plastic tab, and the plastic tab really doesn't feel like it gives much. So I think Milwaukee could have embedded that plastic tab a little bit farther down so it absorbs more force and it's not transmitted to the frame, which is then transmitted to the vials. However, the vials are guaranteed for lifetime accuracy of, I think it's half a thousandth of an inch per inch, 0.029 degrees. So that's a pretty stout guarantee. I don't even know if I have anything that can measure it to that degree to see if they're inaccurate or not. You can just do the standard level spin test, put it on a flat surface, and turn it 180 to see if it's still in, its limits of what it should be doing. All right, so we're going to take a closer look at this thing, and then I'm going to nerd out and talk about why it's so important to have a strengthened core in the center of this thing. So this has a magnesium, they're calling it a backbone. It's just an insert that goes in here and stiffens it up. And that's important because you have this cutout right here with this vial. It helps you with visibility, but it also weakens the whole frame. So they're adding reinforcement. Stabila does the same thing, but they only do it with levels that are over 59 inches long. So this one's 48 inches and it has that reinforcement in it, and I believe the shorter ones do as well. So that's part of the cost difference for the two of them. You've got a lot of extra material in here, and that does make it a little bit heavier too. All right, so here's the close-up on the what Milwaukee's calling the Sharpsite vials, and they are really easy to read from pretty much any angle. You can see the edges of that bubble really well, and they're impact tested. I've seen videos of Milwaukee dropping weights on them, so they're strong. They're not going to shatter easily. And they're also guaranteed for lifetime accuracy. So there's this one in the center. It's really easy to see because of the cutout. And then these two on either side, perpendicular. There's one at the other end, just like this one. One thing you'll note, we've got the end caps here. And these end caps don't actually stick out past the edges of the level. But here, on the level insert on both ends, you have little tabs that stick up, and these stick up barely past where this edge of the level sits. So the reason Milwaukee went with these for the standoff instead of the end caps is apparently Stabila has a patent on their end caps that have little standoffs. So what Milwaukee did is say, well, screw that, we're just going to get around the patent by putting the standoffs right here. And what I really like about this, on the other side, it doesn't have any. So if you want to put it flush up against a surface, you just use this side. And if you want that no slip grip up against a surface, use this side. So you can see it takes a lot of force to get that one sliding, and then with this one it slides smoothly. The handles are really nice. I can get my hands in here with a pair of work gloves on. It's nice and oversized, plenty of room to grab here. And then on the bottom, you've got really strong magnets. You've got 4 spots for them, and they're, approximately about, it's probably about a foot apart, not quite a foot apart each. One thing you'll note, this surface is milled, and it's got like a texture to it. It's got kind of like a swoopy circular pattern across the whole thing. You can kind of hear it when I rub my finger across it. So it's got a little bit of texture to it. It's not super slick. And it's not, it's flat, but it's got these little grooves in it. Just so you know, it's not a perfectly flat milled surface when it comes to the actual texture. When you look at, I put this on the flattest surface I have, my table saw, and I didn't see, any deviation from actual, dimensional flatness, though. All right, so like I mentioned, the magnets on this thing are super strong. Got a metal corner bead on this corner, and you just set it on there and it sticks no problem. And actually you can put it so it's on the edge. You get it lined up, and you can see it rocks around even on that rounded corner and doesn't come off with those magnets. They're super strong. All right, so the only thing I don't like about this level is the eased corners. These are all chamfered. There are no corners that are a straight 90-degree angle. So if you're drawing a line with this thing, it matters if you have a fine tip pencil. It matters what angle you're drawing at the whole time, because if you change the angle you're at, I don't know if you can see that, this line is not straight. And that's because it matters, the level's straight, and if you keep your pencil at the same orientation, it's straight, but when you angle it like that, the lead goes farther underneath that chamfered edge, and you can end up with not a straight line, which I don't like about this. Let's talk about these end caps. They're really interesting. They have some rubber on the outside for shock absorption, so if you drop this lengthwise, it kind of bounces and doesn't put a huge shock on the frame in your vials, which is important. And they are removable, so you see pull on either side here, and you pull this up, and there's a plastic insert that pops up, and this is a compression insert. So when you pull this up, it takes the compression off of it, and the whole thing slides out. So when that little insert is in, when it's pushed down, you can see it pushes apart these two little things right here, and these each have a little rubber circle on them, which goes into this circle on this plastic insert. And this plastic insert also pulls out. You've got to have a punch for both sides of here to get it out, and then you got to have some pliers or something to pull it out, because you can't really get your fingers in here and grasp on both sides. While we've got this cover off, I'll go ahead and tell you why this is designed the way it is. And it's kind of intuitive when you look at it, but I have an engineering background. I'm a mechanical engineer, and the reason this is designed with these big chunks of aluminum in each corner is to maximize its resistance to bending stress. So when you have a beam that's supported, like this level, if you stop it at the floor and then right here and then push down in the middle against it, you're putting a bending stress on it, which is primarily what you're going to end up having on a level like this. There is some shear stress when you do that, but it's primarily bending stress is what it's encountering. And those stresses are greatest at the extreme ends of a beam design. So that's why it's chunky at the end right here, and there's less material here in the middle in the webbing. So there's a little bit of stress here, but most of the stress is in tension and compression right here. So the other reason this is a box instead of an I-beam, where you'd have like a single web in the middle connecting two of these, is a box is much more torsionally stable than an I-beam is. So if you sit here and torque it back and forth, this is going to be a lot more resistant than a simple I-beam design would be. So that's just a little bit of a background, and when you look at a beam, you kind of have an intuitive feeling of how sturdy it is. But that's the mechanical aspect of it. Why is because your stress is concentrated out here where they have the beefiest material. Once again, the way this is designed, it's going to minimize weight while maximizing strength. All right, so I got that little plastic insert out with the help of a putty knife, a punch, and a pair of needle nose pliers. Things in there really good. It's got these little tabs right here on each side that fit into the aluminum housing. So it's really stubborn to pull out, and of course your end cap is still right here. But inside here you can see where the first vial is set, and I was actually surprised this is not metal. That's plastic, and it doesn't even feel like it's glass filled. And I'm really surprised there's a lifetime guarantee on these, just looking at it, and maybe I'm just being skeptical. I mean there is a lifetime guarantee, so they're going to back it up, and I'm sure they did some analysis on how sturdy this is, but this is just kind of set in that channel, and I'm not sure exactly how it's fixed. But I was expecting something that looked a little bit more sturdy than just a piece of plastic stuck in there. All right, so probably most of you don't care too much about the physics and mechanics of materials, about why this has to be strengthened in the center, but I'll get into that a little bit because I like engineering and I like explaining things. For a simply supported beam, that means a beam that has a support here and a support here, and say you have a force in the middle. So we have F here, and since this is static, the supports here are going to have, well, let's just make this simple. We'll say this is 2F and F and F for our forces. If that's in the center, it's symmetric. You've got an even loading like that. So if you look at this, draw beneath this, we have a shear diagram, and this is shear stress across the beam. So it just kind of follows your force, and you have negative 2F, it bumps it down, and you come over here. So this is your shear loading on that beam across the whole thing, and you can see it's even, and then it's even. Now, if you want to look at bending moment, which is where most of your stress comes from in a beam, it's the integral of this. So it does this number up to this and then starts coming back down. So this is actually torque. And so the maximum amount is in the center right here when it's supported on both ends and there's a force in the center. Same with the distributed loading. If you have an even weight distributed evenly across this, it'll be a parabolic curve. It'll be like this. So either way you cut it, this center point right here has most of the stress, like the greatest amount of stress on it. And when you have a cutout like this, you're putting, the weakest point where you have the most bending stress. So it's really important to reinforce it like Milwaukee did in this particular design. In addition to that, when you're looking at this cross section, so normally you have, a full box beam all the way across here, and then you have a cutout right here. And that's also important because not only is the stress the most in the center, it's also the most at the top and the bottom. So when you have a beam like this, and we're looking at cross-section end on, so if I took this level and stood it up on end and looked down it, this will be what you're seeing. And from the center, this is a very simple design, with a box. You can have any type of cross-section, but you have something called cross-sectional moment of inertia, and that's denoted by I. And for this, a simple design that is solid, this is not solid, so it's more complicated, but if you have H and you have width, I is equal to 1/12 H cubed times width. So you get a number out of this, and it's going to be in inches to the fourth or something like that. And the importance about this is your stress profile, sigma, over the area of this cross-section is going to be M, which we calculated here. The highest point of M is in the center, times C over I. And now C is the distance anywhere along here from the center, or the neutral axis, if you have a a symmetric beam, the neutral axis is always the center. So there's no bending stress in the center right here. And at the edge, on the top and the bottom, you have the most bending stress on the exterior. So there's another problem posed when you have a cutout like this, because most of the stress is normally on the top. That's why when you're drilling into a joist, you always drill through the dead center if you can, because when you nick or gouge the top or do a cutout or a notch in the top or the bottom, you're really, really weakening that beam. So that all goes back to point to it's really important that Milwaukee has that, what they're calling the backbone design, which is just a reinforced, I believe it's magnesium little insert right here that goes around that. Because otherwise, if you just have that cutout with no reinforcement, that is the weakest point on your beam if you push down in the center and support it on both ends. So what that stress profile will look like, if this is the top, it will be in compression here, and it'll be in tension on the bottom if you're pushing down. So your stress profile looks like this, with the greatest portion at the extremes. So anyway, all of that to say, it's really good they strengthened this center with the backbone. Probably went way too into detail for most of what you guys are interested in, but for those of you that wanted to know and like to know a little bit more about how, materials are designed and stress comes into play, that's what's going on. All right, so overall, I think this is a really great level, but it does come at a cost premium. And I think it puts it out of the range of pretty much any DIYer. So I'd say this is probably a good buy for pros if you're looking for a level that's going to last you a very long time. But for those of us in the DIY realm, I think it's a little bit too much for budgeting for if you just need a level. If you're not using it day in, day out, and you're using it occasionally, I go with something a little less beefy and durable and less expensive as well, and just baby it a little bit more. All right, so pros out there, I'd love to hear your thoughts on this in the comments section below. Is this worth getting in your mind? Does it have features that you prefer versus Stabila or other competitors out there? I'd love to hear what you think. And hopefully you thought this review was helpful. And once again, don't forget to subscribe.